Sure. So with this introduction, let us look at how to build, what is the general principle of building a latent variable model. So now, general principle for learning a latent variable model. Learning latent variable models. So the principle that we will see now is a general principle that can be applied to all classes of latent variable models starting from GMM2 diffusion model. So we have to look at this one general principle which we will be applying to multiple latent variable models. Now suppose, so what we have is we are given data. We are given data D, which is as usual samples drawn from an unknown distribution IID Px. Now, this is what we have. Okay. And we have P theta is a latent variable model. Let us assume that the latent variable Z is a continuous latent variable for ease of math. So all the equations on the maths that we do is directly extendable to the case where the latent variables are discrete. But now I will assume that the latent variables are continuous and write down the definitions. So now by definition, the latent variable model is a joint distribution between x, which is the observed random variable, and z, which is an unobserved random variable. So let's let the D the latent variable model. Okay. Now what is the goal? The goal is as usual to find out the model parameters, estimate the model parameters theta given D. So this is what our objective is always with any latent variable model. Now how do we estimate theta? So we have the usual framework of finding out theta by minimizing the distributional divergence metric. So minimize the KL divergence between Px and P theta with respect to theta. Okay, so this is what our objective is. We need to find out the model parameters theta that would minimize the KL divergence between Px and P theta. Now what is this equal to? This is equal to, let us write the definition of the KL divergence. See, the definition of KL divergence is integral Px log ratio of Px and P theta dx, this is over x. Now this is equal to, we want to minimize, I will open up the integral. So this is Px log Px. So this, the first term is also called the entropy of data, minus integral Px log P theta x dx. Now I can remove the first term from the optimization because the first term is independent of theta. The first term is independent of theta, therefore I can write this as, I want to minimize negative of integral Px log P theta x dx. Okay, so now this is equal to, if I take out the negative sign outside, then the minimization will turn out to be a maximization problem. The integral that we have is an expectation of log of p theta of x. This is with respect to px, right? Therefore, the theta star, the model parameter that we need, is the one that would minimize the KL divergence between px and p theta. It turns out that minimizing the KL divergence between px and p theta is equivalent to maximizing the expected value of log of p theta of x with respect to px. Now, log of p theta of x is also known as the likelihood function. The likelihood function of p theta of x, or rather you can also call it the log likelihood. Log likelihood. And therefore, this procedure is known as finding out the model parameters by maximizing the likelihood function, and therefore this is called the maximum likelihood estimation. Now note that estimating a model parameter by minimizing the KL divergence between the true distribution or the data distribution and the model distribution boil down to estimating the model parameters by maximizing the expected log likelihood, where the expectation is with respect to the true data distribution. Please remember that this expectation we can compute because we have access to samples from px, and we will use the statistical methods like law of large numbers to estimate this expectation. Okay. Now, yeah, so this is what is called as the maximum likelihood estimation or minimum KL divergence estimation. So now we want to estimate the model parameters theta by maximizing the likelihood. Okay. Okay. So now p theta in our case, in a latent variable model, is given by the following. So p theta of x is the integral of p theta x and z dz, right? And we write the marginal on the data variable as the marginalized version of the joint distribution between the data and the latent variable. Okay. Now let us write this thing as so we want theta star to be that theta which would maximize the expected value of log of p theta of x with respect to p theta. Okay, so let us call this as let us denote the log likelihood function p theta of x with L of theta. Okay. Now what we will do is we will derive a method to maximize the log likelihood. Okay, and then write down the expectation after we devise a method to maximize the log likelihood. Since expectation is a linear operator, one can write down the maxima for one of the data points here and then write down the expectation outside. So what we will do is we'll just consider that we have one data point right now, okay, and omit the expectation for all our calculation. This is just make it a little more less cumbersome. And then once we complete deriving the procedure for maximizing the log likelihood L theta, then we would write down the expectation with respect to px separately outside, because expectation is a linear operator. And please note that the expectation is with respect to px, that has nothing to do with the parameters theta. So we can take down this expectation outside of the optimization. We optimize the log likelihood for like one data point and then write down the expectation outside of the uh, the maximization operator. So that is what we will do. So consider L theta, which is the likelihood of data, log likelihood of the data under the model distribution. So now this is equal to log of integral p theta x comma z dz, because this is the definition of the latent variable model. Now what we will do is, suppose q of z given x denote a distribution over the latent variable. Latent variable z. So please note that in a latent variable model, the latent variable z is not given to us, but we will estimate that along with the model parameter theta. Okay. Now let's say that there exists, so which means that we can take any distribution over the latent variable and we can come up with some optimality criteria to estimate the distribution over the latent variable. Now let's say that q of z given x denotes some distribution over the latent variable z. Okay, it can be any distribution. As I said, we will very soon see that our estimation procedure will also involve estimating this particular distribution over the latent variable, because in a latent variable model we will not only estimate the model parameters but also a distribution over the latent variables. As I said, we will come to that. So now for the mathematical purposes, let's say that q of z given x denote a particular distribution, any distribution on the latent variable z. Okay. So if q denotes that distribution, so now we have L theta, which is the log likelihood given by log of integral p theta x and z. We are marginalizing that with respect to dz. So what we will do now is that we will multiply and divide this integral with q of z given x. Now because q of z given x is probability density function. Okay, so to be precise, denote a density function, over the latent variable z. Okay, let's say that q of z given x is a density function over z. So now since q of z given x is a probability density function, it is always non-negative by definition. Therefore, we can multiply and divide this integral with that non-negative quantity and the integral does not change. Okay, so now what happens is that this is equal to log of integral q z given x times this quantity, which is p theta of x and z, divided by q of z given x dc. Now if one carefully looks at this, what is this? This is a particular distribution over z and this is a function of z. Okay, now product of a distribution and a function, and if you are integrating it over the random variable of that particular density, that particular distribution, then this is by definition the expectation. So this is log of expectation of quantity p theta x and z divided by qz given x. So we are taking the expectation of this with respect to the distribution q of z given x. Okay. So why is this? Because integral of q of z given x times some function, let's say g of z dz, is the expectation of g of z with respect to q of z given x. This is the definition of expectation. Okay, so now we wrote down the likelihood function that we would want to maximize as an expectation. Now observe that we have the log of an expectation. We know how to compute expectations using the statistical estimates, okay, by taking sample means. But here there is a log outside of the expectation. Therefore, no, we cannot estimate the log of an expectation using statistical estimates. So now we want some way in which we write down this entire thing not as a log of an expectation, but expectation of something, okay, expectation of log perhaps. Now the question is, how does one bring out the expectation from the log? So now we have to pull the expectation outside the logarithmic operator here. How do we do that? So turns out that there is an inequality called the Jensen's inequality. It says that for a convex function, rather let me be specific for this. So Jensen's inequality says that log of the expectation of a particular function is greater than or equal to the expected value of log of that particular function. Okay, so this is Jensen's inequality for concave functions. So log of expectation is always greater than or equal to the expectation of the log. So now what do we have here? The log likelihood function that we would want to maximize is now given by a log of an expectation. If we apply the Jensen's inequality to this, we have that this is greater than or equal to the expected value of log of this particular quantity. Okay, now what happened is that we wanted to maximize this with respect to theta. Our goal is to maximize the likelihood function with respect to theta, log likelihood function with respect to theta, and we ended up having a log of an expectation under a latent variable model, but log of expectation cannot be approximated using statistical estimate. So therefore we wanted to write it as an expectation of the log, and we used Jensen's inequality. Once we invoke Jensen's inequality, the objective function that we would want to optimize will not be exact, we'll get a bound on the objective function. So if one can recognize, this is very similar to what we did in the variational divergence minimization on adversarial learning, where we constructed a lower bound on the function that we would want to optimize. Okay, now we have L theta is bounded by, we have the expectation of this particular thing. Let us write this down as some j theta of q. Denote this thing by with j theta of q. So please note that the bound that we have constructed on the likelihood function that we would want to maximize depends not only on the model parameters theta, but also on the choice that we have made on the distribution over the latent variable. Okay, because if you choose a different q, this entire expectation will take a different value. Okay, so now the objective function that we would wanted to maximize adheres to a bound, okay, which would be a function of the model parameters and a distribution over the latent variable. Okay, now the likelihood function is also called as the evidence function. Okay, and this happens to be a lower bound on the evidence, and therefore this is known as called the evidence lower bound. Evidence lower bound. People abbreviate that as ELBO or ELBO. So ELBO. Okay. Evidence lower bound or ELBO. Now what did we do? We wanted to maximize the or find out the model parameters that would maximize the likelihood function. That could not be done because we have a log of an expectation. Therefore, instead of maximizing the function, we are maximizing the lower bound on the objective function, and that lower bound is called the evidence lower bound or ELBO. Okay, and this distribution, now ELBO Q is a function of both the model parameters theta and the density on the latent variable q of z given x. Okay, this q of z given x is often termed as the variational latent posterior. Variational latent posterior. So it's a distribution, it's a density function which is the posterior of the latent variable given data. It is called a variational distribution because the optimization that we are solving here is not only with respect to some parameters theta, but with respect to a class of functions q, or rather a class of density functions. Now the branch of calculus that would describe how to optimize over functions is called variational calculus, and the functions that would get optimized are called the variational functions or variational distributions, and hence the name variational latent posterior. But the point that is to be taken here is that the lower bound that we constructed on the likelihood happens to be a function of both the model parameters theta and the density that we have imposed on the latent variable called the variational latent posterior. Okay, now so far what is the story so far? That we wanted to get theta star that would maximize the log likelihood with respect to theta. Remember that this is the minimum KL divergence estimate, and this under a latent variable model we said that instead of maximizing this, we are maximizing a lower bound on this. We are maximizing the ELBO, which we called as j theta of q. So this was the original maximum likelihood problem. Original maximum likelihood problem, and this is the approximate with ELBO. So we constructed a lower bound on the log likelihood and we simply approximated or rather we will solve the approximate version of the maximum likelihood problem by creating a lower bound on the log likelihood function. Now this optimization of the ELBO involves two things. It involves optimization over the model parameters theta, and it also involves an optimization over the q, the distribution that we choose over q. Okay, therefore the problem that we will be solving is that we need the model parameters theta star and we need an optimal distribution over the latent variables that would maximize the expectation of log of this is the evidence lower bound or elbow that we just created, right? So I'm just expanding it out, and this is with respect to q of z given x. Now this is the foundational problem that is solved in all of the latent variable models that we are going to see now, okay, including the VAE and the diffusion models and so on.